Welcome students. Now I am entering into second law of thermodynamics. Okay. Before entering into second law of thermodynamics, we have studied about first law. Okay, first law of thermodynamics, it's a conservation of energy principle, right? Energy gets converted into heat, energy given gets converted into internal energy and external work. If it's an isothermal process, internal energy will not change. All the heat can be converted into work, we said. Okay, right? Now, that's how it has come. W equal to JH. W equal to JH. J is mechanical equivalent of it. It is 4.18 joule per calorie. Okay, from this formula, what do we understand? Work can be converted into heat. Okay, that is everyday visible in our everyday life also. We don't need any special engines to convert work into heat. Simply rub your hands. Okay, when you are rubbing your hands, whatever mechanical work you are doing, right, gets converted into heat energy. One more example is, you take one stone to a height h, drop the stone into a bucket of water on the ground. Okay, the potential energy of stone gets converted into kinetic energy, right? That kinetic energy, once the stone goes into water, okay, it becomes converted, it gets converted into heat energy, and the temperature of the water will rise slightly. How much will be the temperature rise? Also we can calculate whatever is the potential energy, right? That becomes dq equal to, right, mc dtv, right? We can calculate the change in temperature, however small it may be. Okay, means mechanical energy is getting converted into heat energy very easily. We don't need any engines. But reverse is not always true. Means when I heat my palms, okay, they won't get rubbed automatically like this. Means heat is not getting converted into work that easily. Similarly, when you drop a stone from a height into a bucket of water, water's temperature is rising. But if you put a stone in a bucket containing hot water, stone will not jump to a height h. Why reverse is not true? There is no answer in first law of thermodynamics. Okay. Certain things are never happening in nature. Best example is, why should heat always flow from high temperature to low temperature only? In the very beginning of thermodynamics, what have we seen? Okay, consider an object A here. Okay, an object B here like this. Suppose say this object is at 100 degrees Celsius, this object is at 0 degrees Celsius. Okay, when you join these two, what happens? Heat always flows from high temperature to low temperature. All that we can say, as I told you, heat is a form of energy in transit. Say 50 joules of heat has flown from A to B. Okay, this one's temperature say decreases to 75 degrees Celsius. This one's temperature say increases to 25 degrees Celsius, because this is losing heat, that is gaining heat. This one's temperature increases, this one's temperature decreases. Okay, this is what we observe in our everyday life. Okay, heat is always flowing from high temperature to low temperature. Now the question is, according to first law, why can't heat flow from low temperature to high temperature? Same 50 joules of heat could as well have flown from B to A also. This one's temperature could have become minus 25 degrees Celsius. This one's temperature could have increased it to 125 degrees Celsius. Even then, first law of thermodynamics is satisfied. But we'll never observe this happening in nature. Okay, right? Similarly, as I was giving the earlier example, when you put a stone in a hot water, in a what you call hot water bucket, the stone will not jump to a height. But reverse happens. When a stone falls into water, right, water gets heated up. Reverse is not happening. Similarly, when I bring one hot cup of tea and put it on the table, within 5 minutes or 10 minutes, it is tea always which gets cold, right? Heat goes into room, slightly room's temperature increases. But never it happens that when I bring one normal cup of tea and put it there, room becomes cooler and tea becomes hot on its own. These things are never happening. Okay, but first law of thermodynamics is satisfied anyway. First law is simply talking about conservation of energy, that's all. Work can be converted into heat, heat can be converted into work. It is work which is getting converted into heat, but heat will not get automatically converted into work. We need to have what is known as a heat engine. Means first law of thermodynamics has some limitations, right? It cannot give me the answers or what you call explanations for all things happening in universe. Okay, that's why the need for the second law of thermodynamics. Okay, now if you want what you call heat to get converted into work, we need to have what is known as a heat engine. Okay, without heat engine, heat can never be converted into work. Okay, now how does that heat engine work? How does that heat engine work? Now we'll see what is the block diagram of a heat engine. Okay, the block diagram of a heat engine is like this. Okay, there will be some source of heat at high temperature T1. Okay, I'll call this as source. Okay, right, and there will be our heat engine here, HE, heat engine I'll say. There will be a sink at lower temperature T2. Okay, sink is at lower temperature T2. Now there are two sources of heat, two reservoirs of heat. One is at high temperature, I'll call it as source. One is at lower temperature T2, I'll call it as sink. And my heat engine, what it does is, it takes some amount of heat Q1 from the source at high temperature, right, does some W amount of work and rejects some Q2 amount of heat into a sink at lower temperature. Okay, right, it takes Q1 amount of heat from a source at high temperature, does some W amount of work and rejects some Q2 amount of heat into a sink at lower temperature. This is how basically any heat engine works. Basically any heat engine works. This is known as block diagram of a heat engine. It is taking Q1, it is doing W, it is rejecting Q2 amount of heat. Here again, first law of thermodynamics should be satisfied. That is, energy should be conserved always. There is no exception for that. Okay. Now, say it is taking 100 joules of heat. Okay, and is converting that 40 joules into work. Remaining 60 joules must get rejected into the sink at lower temperature. There is no exception for that. First law of thermodynamics should be valid always. Okay, should be applicable always. Okay. Now, I'll define what is called efficiency of a heat engine. Okay, how do we define efficiency? What is the general definition of efficiency? Forget about heat engines, refrigerators, other things, etc., etc. What is in general? How do you define efficiency? Output by input. Output by input is known as efficiency. Okay, so efficiency eta is, right, output by input, right? What output we are expecting, okay, what input we are giving. From a heat engine, what do you expect? We expect work as output. So this output is nothing but work output. Work output. Okay, in order to get that work from the heat engine, what is that I'm giving as input? Some heat energy I'm giving. That is, this input is nothing but heat input. This input is nothing but heat input. Okay, efficiency is always output by input, we call. Okay, example, need not be efficiency of a heat engine only. Okay, say student's efficiency. How do a teacher finds the efficiency of a student, right? His teacher will be giving same lecture to all the 40 or 50 or 100 students in the class. Okay, same lecture is going. Suppose in the end, when exam is held, right, so one student got 90 out of 100, other student got 40 out of 100. In that aspect, the student who got 90 is more efficient than the student who got 40 in that aspect. Okay, because input is same for both. Okay, whoever gives more output is known as more efficient. Okay, similarly, right, anywhere efficiency is output by input. What output, what input. For a heat engine, the output expected is work. For the input we are giving is heat. Okay, now what is that work output? W is the work that is coming out of the heat engine, and what is the amount of heat I am giving? Q1 amount of heat, that is heat input. Okay, W by Q1, right? Now from conservation of energy principle, right, it is taking 100 joules, converting 40 into work, remaining 60 is going into the sink at lower temperature. That is, what is Q2 equal to? Q2 equal to 100 minus 40, 60, that is Q1 minus W. Okay, Q1 minus W. So what is W equal to? W equal to, right, it is Q1 minus Q2. It is taking Q1, rejecting Q2. What is happening? Remaining energy is getting converted into work. So W can be written as Q1 minus Q2. So the formula for the efficiency of heat engine will be Q1 minus Q2 by Q1, or simply 1 minus Q2 by Q1 we write. This is the efficiency expression in general for any heat engine. Okay, what is Q1? The amount of heat given as input. What is Q2? The amount of heat which got rejected into the sink at lower temperature. Okay, keep that in mind. Q2 is very important here. Q2 is the amount of heat that is getting rejected into the sink at lower temperature. Okay, right? This is in general the efficiency of a heat engine. Efficiency is denoted by eta usually. Okay, now there is something known as refrigerator also. Okay, what is a refrigerator? How do we define a refrigerator. A refrigerator is one which keeps on whatever thing, domestic refrigerator, whatever you put inside the refrigerator, it will make them cool. Okay, so what is that here refrigerator doing? Refrigerator is something is becoming cold, means somebody must be taking heat from it, isn't it? So what does a refrigerator do? Refrigerator takes out heat from whatever you put inside, milk or tomatoes or aloo or potato, whatever it is. Okay, it is taking out heat from what you call the things which we keep inside and is rejecting heat into the surroundings. Okay, that's how it makes things what you call cooler when we keep them inside the refrigerator. Okay, now here how do we represent a refrigerator? Refrigerator, it is like the block diagram of a refrigerator is like this. There will be a source at high temperature, okay, T1. Okay, this I'll call it as a refrigerator RE, and there will be a sink at lower temperature T2, same as before. Okay, now refrigerator works in opposite to that of a heat engine. Okay, to some extent what will it do? Heat engine takes heat of Q1 heat from a source at high temperature and rejects Q2 amount of heat into a sink at lower temperature, whereas a refrigerator takes Q2 amount of heat from a sink at lower temperature. Okay, and I have to do some W amount of work on the refrigerator. What that refrigerator does is, whatever work I have done, W plus whatever heat it has taken Q2, it will reject that into source as Q1. So what is Q1? Again, first law of thermodynamics should be valid here also. So what is Q1? Q1 equal to the amount of heat it has taken from the sink at lower temperature plus the amount of work I have done. Okay, Q2 plus W becomes Q1. That Q2 plus W, right, as Q1 gets rejected into source at high temperature. Means a refrigerator is taking heat from an object at lower temperature. Upon doing some work, somebody has to do some external agency has to do some work on the refrigerator. Then what is that it is doing? It is it is taking that heat Q2 and W and is rejecting into source at high temperature. Here also first law of thermodynamics is satisfied. Okay, it takes 20 joules of heat from the source at low temperature. I am doing some 50 joules of work on it. So what is this refrigerator doing? This 20 it has taken plus 50 I have done. 20 plus 50 put together 70 joules of heat is getting rejected into the source at high temperature. Okay, right, now how do we, for every engine we need to have some efficiency term, but efficiency term is used for heat engine. For a refrigerator we use the word called coefficient of performance. Okay, coefficient of performance, COP, we write. Coefficient of performance, COP, it is usually denoted by beta. Eta is reserved for efficiency, beta is reserved for coefficient of performance. Okay, right, now here also, what is the output I'm expecting from a refrigerator? What do you expect from a refrigerator? It has to keep things cool. Whatever is put inside, it should make them cool. Okay, right, means it has to take as much amount of heat, right, as possible from the things which we are keeping inside or from the sink at lower temperature. That is beta equal to, right, Q2 is what I'm expecting. The greater the amount of Q2 it takes, the good refrigerator, because things will become cooler and cooler inside. Okay, Q2, in order to for it to extract that heat from sink at lower temperature, I am doing some W amount of work. This is the input I am giving. Okay, so Q2 by W is the general formula for coefficient of performance. Okay, now again, what is W equal to? W equal to, take this W, bring that Q1 to this side. Okay, so what is W equal to? Q1 plus Q2 equal to W, or W equal to Q1 minus Q2. Okay, Q2 we take to the other side. So beta equal to, right, Q2 by Q1 minus Q2, right? This is the most general expression for the coefficient of performance of any refrigerator in general. Okay, so efficiency of a heat engine is Q1 minus Q2 by Q1, or 1 minus Q2 by Q1. Okay, coefficient of performance of a refrigerator is Q2 by Q1 minus Q2. Okay, so far so good. Now what is the relation between Q1 and Q2? They'll ask. Okay, right, what is the relation between eta and beta? Okay, if eta is given in terms of beta, how do we write? Or if beta is given in terms of eta, how do we write? Means we have to find out relation between eta and beta. Okay, right, okay, that manipulation part aside, now here we'll get some doubts. Okay, everything looks fine here in the case of a heat engine. Okay, it is taking Q1 amount of heat. It is taking Q1 amount of heat from a source at high temperature and rejecting Q2 amount of heat into a sink at lower temperature. Remaining Q1 minus Q2 difference is getting converted into work. Now, can we expect any heat engine to take what you call 100 joules of heat energy? Okay, 100 joules of heat energy and doing 110 joules of work. Can we expect any heat engine to take less amount of heat and do more amount of work? Just guess. Okay, can you imagine a heat engine which takes just 100 joules, right, and doing 110 joules of work? What is the problem if I say that I have created one engine like that? That engine is impossible, we say. Okay, why? Because it is violation of first law of thermodynamics. Okay, first law of thermodynamics, energy should be conserved. No engine can take less amount of heat, right, and can do more amount of work, because energy violation, energy conservation principle gets violated. Okay, such an engine, no lifeless engine for, okay, that's inanimate engine or lifeless engine. That's important here. See, engines with life, you and me sometimes will do some work without taking any input. Okay, without eating for one day also we can run for 10 kilometers. Okay, what is happening there? I am spending my internal energy. Okay, I am an engine with life. Okay, we are also engines only with life, but we are talking about inanimate, lifeless engines. Okay, no lifeless engine can take less amount of heat and what you call do more amount of work, because first law of thermodynamics gets violated. Okay, that is what is happening here. Eta equal to W by Q1. W is 110, right? Q1 is 100 only. That eta will be greater than 1. Okay, eta greater than 1. If somebody says that, right, there is an engine where whose eta is greater than 1, right, we can simply reject that claim as not possible. Why? Right, eta cannot be greater than 1. It is a violation of first law of thermodynamics. No inanimate engine can take less amount of heat and convert more amount into work, more energy into work. Okay, right? Now, inanimate engine, right, that is called perpetual motion machine of first kind. Perpetual motion machine of first kind. So according to machine of first kind, we write, okay, according to, this is known as Oswald statement, okay, of first law of thermodynamics, right? For perpetual motion machine of first kind is impossible according to first law of thermodynamics. That is known as Oswald statement of first law. Okay, what is perpetual? Perpetual means everlasting, ever running machine, a machine which continuously, once or twice, some engine with life may take some less energy and do more amount of work, but it cannot keep on continuing the process forever. It is not possible. Okay, so everlasting or continuously running engine, perpetual motion machine means continuously running engine of first kind. What is that first kind? Right, an engine which takes less amount of heat and doing more amount of work is impossible according to first law of thermodynamics. That is, eta greater than 1 is impossible according to first law of thermodynamics. Okay, that is according to common sense only, we all accept that. But now my doubt is, why can't a heat engine take 100 joules of heat and convert all that 100 joules into work? What is the problem? First law of thermodynamics is happy only, no? Okay, first law of thermodynamics is happy only, right? Some engine is taking, right, Q1 amount of heat and it is converting all that Q1 100 joules into work. Okay, what is wrong? First law of thermodynamics satisfied, right? The eta is equal to 1, W equal to 100, Q1 is also 100, so eta will become equal to 1. But we will never observe such an engine also. Okay, no inanimate engine, no lifeless engine can take some amount of heat and convert all into work. Okay, it is impossible. That is, eta equal to 1 is also not observed in nature. Okay, not observed in. Why? There is no answer in first law of thermodynamics. It is perfectly okay for first law to take 100 joules and convert all 100 joules into work. But we are never observing, we have never observed an engine which is doing like that. Okay, that is, eta equal to 1 is also not observed to be practical. Okay, here comes the second law of thermodynamics. Okay, the most important, the most fascinating law in thermodynamics or entire physics is second law. Second law says, right, perpetual motion machine of second kind is also impossible. Okay, what is that perpetual motion machine of second kind? Okay, an engine which takes, right, some Q1 amount of heat and convert all that Q1 into what you call work W. That is, eta equal to 1 is also impossible according to second law of thermodynamics. Second law says, right, eta equal to 1 is also impossible. Eta greater than 1 is violation of first law of thermodynamics. Eta equal to 1 will become violation of second law of thermodynamics. Okay, right, this is known as Ostwald statement. The second law was visualized by different scientists in different ways. Okay, Ostwald has given one statement for second law of thermodynamics. Kelvin has given one statement, Planck has given one statement, and later on what scientists did is Kelvin and Planck statements, they have merged together into one statement called Kelvin-Planck statement. It is based on a heat engine. Because those definitions are almost similar, they have combined those two and have given us what is known as Kelvin-Planck statement. So Kelvin-Planck statement talks about an ideal heat engine. What is an ideal heat engine? Okay, perpetual motion machine of second kind. What is that perpetual motion machine of second kind? Okay, an engine which takes 100 joules and convert all 100 joules into work. Okay, that is impossible according to second law of thermodynamics. Okay, right, now Kelvin-Planck statement talks about heat engine. There is one more one more scientist, Clausius, has given another statement for second law in terms of refrigerator. Okay, in terms of refrigerator. Then later on Clausius has introduced a new concept called entropy. Okay, he has introduced a new term in physics known as entropy, and in terms of entropy he interpreted second law of thermodynamics. Okay, that is Clausius statements. There are two statements for second law by Clausius. One is based on refrigerator, other one is based on entropy. Though there are different statements for second law of thermodynamics, remember all statements ultimately lead to the same fact. Okay, if they look differently, but if you are violating one statement, you are automatically violating other statement also. Okay, now, right, we'll see what is Kelvin-Planck statement. What is Kelvin-Planck statement? According to Kelvin-Planck statement, no lifeless engine or inanimate engine can extract heat from a source at high temperature and convert all into work W without rejecting any heat Q2 into a sink at lower temperature. That is, without rejecting any heat into a sink at lower temperature, no engine can take some heat and convert all into work. Means Q2 is a must according to second law, means some or the other heat must get rejected into the sink. Without rejecting any heat into a sink at lower temperature, it is impossible for an engine to extract heat and what you call from a high temperature source and convert all into work. Means Q2 cannot be 0. Okay, you cannot make Q2 equal to 0. When you cannot make Q2 equal to 0, right, eta will never be equal to 1. Eta is less than 1 always. Means according to Kelvin-Planck statement of second law of thermodynamics, okay, for any heat engine, however ideal it may be, eta greater than 1 is impossible. First law itself rejects it. Eta equal to 1 is rejected by second law of thermodynamics. According to second law, eta is always less than 1. Eta is always less than 1, because without rejecting any heat into a sink at lower temperature, it is impossible for any engine to, right, extract heat from a high temperature source and convert all into work. That is known as Kelvin-Planck statement of second law of thermodynamics. Okay, right. So the another way stated, perpetual motion machine of second kind is impossible. What is perpetual motion machine of second kind? That's known as Ostwald statement of second law. Something taking some heat and converting all into work. Okay, Kelvin-Planck statement extends it further. It says that both are one and the same. Okay, it says that every heat engine has to take some heat and convert some into work and reject some Q2 into a sink at lower temperature. Q2 cannot be 0. When Q2 cannot be 0, Q1 becoming infinity is anyway impossible. Okay, nothing can be infinite in physics. Okay, so right, when Q2 is not equal to 0, eta cannot be equal to 1. Eta should always be less than 1. Why? Again, there is no answer. Okay, again, there is no answer. Why a heat engine has to reject some heat into a sink at lower temperature? What is the problem if it takes 100 joules and convert all 100 joules into work? Second law says it is impossible. Second law says it is impossible. Okay, right, now there is another statement of second law in terms of refrigerator I told. Right, now that statement is given by Clausius. Okay, according to Clausius statement, no lifeless engine or inanimate agency, right, without the help of external agency, no lifeless engine can transfer heat from a low temperature reservoir to a high temperature reservoir. Okay, the wordings may change slightly here and there from the textbook, but the meaning is same. Okay, right? It is like that. Without the help of an external agency, right, no lifeless engine can transfer heat from a low temperature sink to a high temperature source. Means transferring heat from low temperature object to high temperature object is impossible without the help of external work. Means heat by itself cannot flow from low temperature to high temperature. If you want heat to flow from low temperature to high temperature, it is not possible on its own, or naturally it is not possible. You have to do some external work. Without the help of external agency, without somebody doing external work on it, right, it is impossible to transfer heat from low temperature object to high temperature. That is, W is a must. Okay, W cannot be made 0 in the case of refrigerator. Okay, means if I can make W 0, what happens to beta? Beta becomes infinity. Okay, coefficient of performance becomes infinity. Coefficient of performance of a refrigerator can never be infinite. It is always finite. Means it is always less than infinity. Means W is not equal to 0. W is not equal to 0. These are the statements given by second law of thermodynamics. That's what we observe in nature also. In the universe, certain things are happening. Okay, I drop this pen, that pen always falls down. That pen always falls down. Not even a single day on some festival day or January 1st or something, the pen goes up. Okay, it is not possible. Why? Right? Means, of course, you say, sir, we have studied in our +2 level that gravitational pull. Now the question is, why gravitation should pull always? Why can't it push? Okay, no answer. Right? You take one chalk piece. That chalk piece, if you drop it, it falls on the floor and breaks into 3-4 pieces. Never you observe in nature 3-4 pieces of chalk piece coming together, becoming into a single piece and coming back to my hand. Is it possible? Impossible. Okay, you drop some egg or a cup of tea. They always fall down, break into 3-4 pieces. But a broken cup will not gather itself up and comes to your hand. Impossible. Okay, unless you are a movie hero, right? These things are not possible in nature. Okay, why? Means we have to search for the answers in second law of thermodynamics. Second law of thermodynamics says such a refrigerator is impossible. Such a refrigerator is impossible. Similarly, the same second law says in terms of heat engine, okay, without rejecting any heat into a sink at lower temperature, no heat engine can take some heat and convert all into work. These things are impossible. Okay, right? Later on, Clausius himself has generalized, he has introduced another term called entropy. Okay, right? For the first time, right, he introduced something known as entropy as a concept, and based on that entropy, he has generalized the second law of thermodynamics. Okay, right? Those things will be covering in the next video. Thank you.